Hi. So we're going to talk about time-consuming algorithms. Maybe you've met some. First of all, let's get to know each other. So I'm Laurent Picard. You can follow me on Twitter. My handle is Picard Paris. So my name is Picard. I live in Paris. That's why. I'm a software engineer, and I joined Google a few months ago. And I work for Google Cloud Platform. And in previous life, I created Bookin. So that's an ebook company. I've been working for 17 years in the ebook market. So I'm one of the ebook dinosaurs. I worked in hardware and software. And with Bookin, I created a highly available ebook ecosystem. So ebook device, ebook apps, and ebook stores as well. And a long time ago, in 1999, I co-created the first ebook device in Europe. But I'd like to have a sense of who you are. So just a few questions. So among you, who are developers? Nice. So let's say 3/4. Who is already using cloud services? Okay, 2/3. That's pretty common. Who has already used Hadoop or Spark? Okay, less and less. Let's say 50%. And who knows BigQuery? Okay, so a few. So before we start, I'm going to make you a promise. Sorry, we're going to so here are the takeaways I wanted you to have today. So we're going to talk about time-consuming algorithms. We're going to see how we can run this algorithm in parallel. We're going to see how you can stream the results from this code. And we're going to also see how you can analyze the result in real time. Okay? And here's the promise I wanted to make you before we start. No computers are going to be harmed during these sessions. So I tagged it serverless. Well, so what does it mean? I came here, I only have my laptop, right? And we're going to use a lot of computers during this session. And they're not there for the time being. They're somewhere just sleeping. And I have not configured anything except that I have an account. And I have code that I prepared for you. Okay? So let's start. So first example, I'm pretty sure you have made that. You have a computation that's going to take an hour. So as a developer, the joke that you make most of the time is the following: okay, that's coffee time. I'm pretty sure you take the chance to have coffee. I like coffee, but after some time, it's going to be maybe too much. Also, maybe you're going to take this as an opportunity to do something else. So you're going to lose focus and be less efficient. And so your work is going to be fragmented. So let's try to find a solution to that. As of today, all of our computers have several CPUs, so logical CPUs within the same core. So if I take this example, I have a 1-hour computation. If I can cut it into 6 chunks, so I'm going to end up to be able to run my computation, my 1-hour computation in 10 minutes, right? I'm going to run this 10 minutes over 6 different cores. But what if my computation takes 1 week? So in this case, I'm not going to be able to do it, even though I have a few servers at home or in my company. There's no way. In the best case, it's going to take maybe a few days. So there are really side effects when you're dealing with such time-intensive workloads. You have a broken schedule. So it has a big impact on your project as a whole. Let me give you an example. So back in Bookin, we had some huge metadata coming from publishers, so gigabytes of data, and you had to process them. Sometimes you had to fix them. And I had a batch that took 2 days, and there was no way I could do it differently at the time. It took 2 days. So it's bad in some ways. So first of all, you have to wait for 2 days before you get an actual result. So that's not very efficient. And also, when you're starting to implement your solution, most of the time you have bugs. So when you realize that you have a bug and you just spend 2 days on a computer to process your data, let's imagine that you just wasted 2 days. And worse, computers sometimes fail. And if you're just running out of memory or whatever, after 1 day and a half, then you just wasted 1 day and a half again, okay? So this is just to give you an example, and by experience, when you have such delays, you are just generating additional delays as a project manager. And this has an impact on the users as a whole. So for instance, in the case of an ebook catalog, users could be waiting for 2 days to have an up-to-date catalog or to have up-to-date reviews. Not very good, but it could be worse. If you're a searcher, you're working, let's say, on finding a cure for a disease. If you're wasting weeks like this, this is not going to be very fast, and worse, there are some users that are waiting for you to get this cure. So here, the clouds have quite a few CPUs. So if I'm taking this time a 1-week computation, I split it into roughly 1,000 chunks. Then I'm going to get back to my 10 minutes. So I calibrated this presentation for 10 minutes because this is roughly what it takes me to get a coffee, 10 minutes, okay? So one solution to distribute our code is Spark. So with Spark, basically, you can run it locally, but then you can distribute your code on a master node and on X worker nodes. So here we're talking about servers or CPUs or virtual CPUs. The nice thing is that it's an open source project maintained by Apache. There are many contributors. You can get it to run in Python, in Java, in R, and in Scala. So I think it covers many of your use cases. And this is pretty fast. It's, let's say, if you compare it to Hadoop, let's say it's an optimized version of Hadoop. I'm being very basic here. And it's processing the data in memory. And so as a whole, it's 10 to 100 times faster than Hadoop, okay? So here we have an open source solution to distribute code. We'll see later how we can do it. But we are going to need CPUs, right? So another solution, a complement to that, is Dataproc. So Dataproc is a module within the Google Cloud, and it's actually a managed solution for the Spark service. And this is why, again, you're hearing or reading about serverless. And as you can guess also with Google, this is highly scalable. So as we say, a picture is worth 1,000 words, but in my opinion, a live demo is worth even more. Okay, so let's have a live demo together. So I took this example for a time-consuming algorithm. So we're going to try to estimate pi. Can you raise your hand? Who knows exactly what this is about? I'm pretty sure many of you have seen it. Okay, okay. So I'm going to explain a little bit what it is. Yeah, you can read the code. Okay. So this is a mathematical statistical experiment. You take darts, many darts. You have a square. You draw a circle within the square. It works with a quarter of a circle too. It's the same. You throw the darts randomly, and you keep the darts. You count the darts that are within the circle. If you throw many darts, you are going to go closer and closer to estimating the surfaces of the circle and the square. And the ratio between the two is pi over 4. So if you just reverse the equation, you get here how you can estimate pi just by counting the dots that are inside over the total number of dots that have been launched. Okay, you can have a look on YouTube. There are nice guys who took a journey in a park, and during one whole day, they tried launching actual darts. It was not random, so they struggled, but they roughly came, after launching hundreds or maybe thousands of times their darts, roughly they came to an estimation of 3.1. But at the beginning it was 2, 3, or 4 only. So it's a very slow it's a very slow method to estimate pi. In this case, I calibrated it this way. I am taking 10 million samples. So I am throwing 10 million darts, and on my computer it takes roughly 5 seconds. Okay, so this is the code that you saw. I just added some output. I'm going to launch it. Okay. So let's wait a couple of seconds and just to make sure that you're seeing the result. Okay, so in 6 seconds, I launched 10 million darts and I got 3.14, which is okay. But this is random. If I run it again, maybe I will get 3.2 or 3.0. Okay, so now if I have the same algorithm, but I'm going to run it many times. So let's say 1,000 times. So this is going to take 5,000 seconds, so over an hour, okay? So I'm not going to run it because obviously you understand what it is, but just to show you here, I'm just repeating the same experience 1,000 times, okay? So now we're going to start distributing our code to be able to make this 1 hour experiment in a short time. So for that, we're going to create a data prop cluster. So that's a Spark cluster with a worker node and, with a master node and worker nodes. So here I'm going to use the web console and I'm going to create the cluster. So to make it under 1 minute, we're going to choose 256 CPUs. So I'm choosing the region. It's going to run in Europe West, so that's in Belgium, actually. I'm going to keep the master node as a standard machine. I don't need a disk, so I'm going to put the minimum 10 gigabytes. And I said I'm going to choose 4 times, so 4 workers of 64 CPUs. So that should be 256. And I'm also going to choose the minimum size for the disk. Okay, and that's it. I create the cluster. It's going to take a minute, about a minute, a big minute. It's between 60 and 90 seconds. And during this time, we're going to see how we can prepare our code to run it in parallel in this cluster. So I take my small experiment here. You have to realize that this time we're using the random method, and it's going to run on many CPUs. So I need to make sure that I'm not using the same random values otherwise I will get exactly the same result. So here I have just adapted the method to get a random seed. And this way, I will make sure that I'm not getting the same result everywhere. And then this is just Spark. So I will not get into details, but Spark allows you to create an RDD, a resilient distributed data set. So this is an abstraction to allow you to run your code. The method here, map, is the one that is going to distribute my algorithm, so the Monte Carlo Dart experiment, over all the cores. And then when everything is finished, I'm going to reduce, and so by adding all the results all together. And like here, I will get all the darts that are inside with just this simple call. And the final result is just computed the same. So here, the cluster is about to be finished. Okay, So you can see it's consuming very little, 1%. OK, my VMs are ready. So you see I have my master node and 4 workers of each 64 CPUs. I'm going to SSH. So here, nothing existed before that. This is very convenient. This is SSH within the browser. So this is a Chrome window that's being opened. And I'm going to have access to this virtual machine. And so it takes a few seconds. I'm going here just to copy-paste the code you saw. OK, just copy everything. So here I have my window on the master node. I'm going to launch PySpark. So this is Spark for Python. So likewise, it takes a few seconds to boot. And I'm going, so this is a console within PySpark, and I'm going just to copy and paste the result, my code, sorry. OK. So here, it's like a Python console. I paste. OK. And here, what you see is that I didn't provide many settings. So by itself, my algorithm is being distributed. So it hasn't started yet. It's uploading the code everywhere. And OK, and now you see the results coming back to my master node. And here, this is what remains to be distributed. And maybe there are a few reminders before it's actually finished. Yeah, and this is the end of my code. And here you see I get pi is 3.1415. And I used this time, in 39 seconds, I launched 10 billion dots. So that's one way. So let's exit. So here, everything is manual, as you can see. I'm going to delete my cluster, because there's no point in keeping all these CPUs. OK. And now we're going to the next stage. So what we've done is we've launched 10 billion dots, but we didn't keep the results, so everything is lost. So the next step is to keep everything in a database or a data warehouse, and BigQuery is the other solution. It's also in Google Cloud, and it allows you, like a database, but scalable and real-time. It allows you to keep all of your results very easily. So here I have nothing. We're going to create it. I'm going to enrich my metrics. So here I'm going to specify a timestamp, a duration for each experiment, and my main result, how many darts are inside and how many darts have been thrown. So this is how we are going to create this data warehouse. So this is a Python code, this one. So you see this is exactly the code I showed you. I'm going to launch it. OK, so that's number 5. Sorry. OK, so here the small Python code is going to create the data set because it doesn't exist, and then one table within this data set. So it should come. OK, the data set is created, and the table. So let's have a look. In BigQuery, so I'm going to refresh my project. OK, so here I have my Monte Carlo data set. And within that, I have my experiment table. And here you find the schema. So now I have a data warehouse, and we can push data to that. So the next step now is the experiment, but the one that is going to last for 1 week. OK, so I hope you have your sleeping bags and everything, right? You didn't get the memo? OK. So the next step is to create, this time, the same cluster as before, but to go faster, we're going to create a cluster with over 2,000 cores. Okay, so this time to show you also how you can better integrate, for instance, with continuous integration, we're not going to create the cluster manually, we're going to create it with a simple command, like here, gcloud dataproc clusters, so that's the main command prefix for everything related to clusters, and here we're going to say, okay, create cluster 2048 in this region, and let's have a master node like this with 8 CPUs, and let's have 32 64 CPUs worker nodes. So I'm going to copy paste the command, and here, okay, let's do it. So this is just like before, but this time it's going to run for 60 to 90 seconds in parallel. And during this time, we're going to see the next step is to keep adapting our algorithm. So here you can see that I have added a timestamp at the beginning of my algorithm. Then I am also computing the duration of my experiment. And instead of returning the single result, I'm going to return my 3 metrics. And here, the main loop is just adapted slightly to be able to collect at each increment, each iteration, my result. So here, I'm still calling map on my Monte Carlo experiment, but instead of computing the result, I am collecting the result. And here, I am building rows. I am streaming the rows to BigQuery. So let me show you the whole code. Okay, so this is what you saw. Here I have a method to stream to BigQuery. So basically I am just making JSON data. And here by calling that BQ insert, I am throwing all of my JSON. So roughly every 5 seconds, I am going to stream all of my JSON data to BigQuery. And again, with continuous integration, here I made a slight change. I am going to use that as a job. So I'm not going to log in into PySpark. I'm going to launch a job to PySpark directly. So I don't have to connect to the console anymore. So let me show you how it looks. So gcloud dataproc jobs, and here I'm going to submit a Python Spark script to this cluster, and just by specifying my Python code. Okay, so before that, let's check. Yeah, I have my 2048 core cluster. So here it's waiting for me to get something to work on. So as you can see, the worker mode, so I want SSH into this VM this time. And I have all my workers with 60 core in each VM. Okay, so let's copy paste the command. So you understand, this is my job here. So this is the algorithm that we've been enriching every time. And I'm going to launch this job here. Okay, so the measure command is a Windows command to measure everything. So you see, I'm giving my Python script to this cluster, and I specify that it's a Python Spark script. Okay, so let's wait a little bit. So right now, it's being distributed to 2,000 cores, just like before, and the job is running. So here the code is getting everywhere, and we're beginning to get results. Okay, and there are many stages that are going. I think there are around 50 iterations that are going to be run. Okay, let me check that. Okay, So it means that we are already getting results. So let's check now in BigQuery what we have. So BigQuery, as I told you, is a data warehouse, but it's like a SQL database. So we're going to query this this table. So let me show you what we can do. Okay. So let's have a look, at all the data that we have. So with this simple query, okay. So the data are being streamed live to this table, and I can query it in real time. So here we have already 12,000 experiments that have been run. You can see the duration for each of them, the timestamp at the start time of each experiment, and you can see the results. Okay. We're streaming live. We are querying it in real time, and then you know better than me. I guess many of you are data scientists. You can do whatever you want on the partial results, and of course, in a couple of minutes, everything will be finished. But so I must have a few dummy queries. Let me check. Yeah, here. So, for instance, I can have a sense of the result, an estimation. So here, as you can see, I know that pi is between this value, and on average, I have this. So, which is already quite good. And let's try another one. Saved queries. Okay. You can also, if you know SQL or equivalent, you can get an estimation of the different percentiles. So the nice thing is that with all the metrics that you can stream, then you can analyze pretty much anything. So here with the quantiles method, I am going to ask, okay, give me the first 10% of the results and strip everything like an histogram. So let's run it. Okay, so you see it's very fast in 2 seconds. And so here again, if I was to draw an histogram based on this, you get a sense of the different values. And let's run the last one. Also for the duration, because this is running on virtual CPUs, so you have no idea what's going on. So here I wanted to have an idea about what's happening for my different experiments. So let's run this, and I will have a pretty good idea about the different durations. So here, as you can see, it's running between. So some experiments are going very fast. So this is inherent to the PySpark overhead. So some are going very fast, but most of them are going between 5 seconds to 8 seconds. Okay, and you can have the distribution. So let's have a look at the. I think we are starting to see the end of the experiment. Here you can see the job that has been launched. So you have an history. You can check everything later on. If there's an error, you can check it here. Here you still have all my instances. And what's happening here? Okay, no, it's going to take a bit more time to finish. But as you can see, we have been able to get results, analyze in real time, and the experiment is still ongoing. And it could go for hours, but actually hours here represent weeks. Okay. So to wrap up, here are the main resources you need to know. Spark, so at apache.org, Dataproc and BigQuery are under the cloud.google.com main site. And I hope you've. So my goal by coming here was to inspire you. I hope this gave you a few ideas of how to accelerate your developments and getting results faster, feel free to ping me on my Twitter. If you want this code to be open sourced or whatever, if you want, I could put it on GitHub. This is my first talk about this subject. And I joined a few months ago. So 3 weeks ago, I barely didn't know about Dataproc. So this is just to tell you how fast you can go up to speed with this technology. OK, so that's it for me. Thank you very much.
Thank you so much. Any questions to Laurent regarding Dataproc or Spark? OK. Yeah, there's a question.
Most of the computations require some kind of external libraries or other dependencies. And does this product support custom images or something like this when deploying workers?
I think so. I've not played with it, but it does support by standard all the mathematical, so NumPy and so on. So if you're a data scientist, it will work right away. And by the way, here I have seen. So my code is not optimal. It could go a lot faster. I have an overhead because I am streaming the data every 5 seconds, so I could do it differently. And likewise, the random method I'm using is not really that good. It's not that random. So I could converge to the right result a lot faster, and by that I would need to use NumPy, the NumPy library. So I can do it, but here I wanted to stay as simple as possible. So this is why I kept that code. But I will check on and will publish on my Twitter account your question. So do you have an idea about which, do you have a library in mind maybe other than NumPy? Or? Okay, I'll check. I'll check that.
Okay, so you can connect on Twitter about that. So Laurent, thank you so much for coming and thank you for your talk. We have a break right now. Longer break. There's coffee out there.